Right, last time I was talking about triangles. I can just spend a bit of time on quadrilaterals. A very common form of a quadrilateral you'll come across will be a parallelogram, which in general like something like this. Okay, so a rectangle and square are also come under this family as well. The important point is that they have two sets of parallel lines. This line is parallel to that, and that line is parallel to that. So that's just the definition of a parallelogram. But there's various properties that should be stated. First, fairly, well, I would say trivial, but first one to say is that opposite angles are equal. Now, secondly, these two diagonals will meet, will basically divide each other. Okay, so that's each they divided each other into two equal parts, and that's so for that's fairly obvious for things like squares and so on. But yeah, that's the rule for all parallelograms. And thirdly, the other one I want to mention finally is the fact that these triangles here are congruent. You would need to flip them over. You need to take that triangle and flip it over, but the two triangles will fit over each other, so therefore they are congruent. Now, if I know what the length of this side is, the area of something like a rectangle is just a times b, as we've already stated. But the area AB is not going to be the area of this parallelogram in general. Now, you could take this triangle and work out the area of that triangle, half AB sine, well, theta there, okay. That would be the area of that triangle, but because I've said that these are congruent, therefore they have the same area. So the total area of the parallelogram will be twice that. So if I could just, hopefully you can understand what I'm doing there. That's the area of the parallelogram, just that there. AB sine theta. So if you have that angle, well, obviously if you have A and B, then you'll be okay. You'll be able to work out the area of the parallelogram. So two special cases. Well, you class this in general. Okay, I've said that the family is called the parallelograms, which includes a square and a rectangle. But an actual special case like this would be classed as a rhomboid. But a rhombus is one where the sides are all equal. That has a couple of features over and above what the features I've just mentioned. Well, you have to excuse me here. This is very rough and ready. But what will happen here is that these diagonals will intersect at right angles. Okay, you've got 4 right angles there. And furthermore, additional feature for a rhombus is that well, I'll use a different letter altogether, is that it intersects the angles of the rhombus itself, i.e. the lines of intersection, the diagonals intersect the angles of the rhombus. You've still got to, I mean, it's taken as read that the lines intersect so that they divide each other. I mean, the lengths of the intersection, the lengths of the diagonals are different, so that length will be different from that length still. But you've got right angles at the centre of the intersection and the bisection of the angle of the rhombus. If I consider a square, that has all the properties of the parallelogram and the properties of the rhombus, intersecting, bisecting the line. But this has the additional property that these these lines here are all identical. So actually, you've got four congruent triangles now, but that's for a square. In a non-mathematical sense, these rhombuses and these rhomboids, are sometimes referred to as diamonds. It probably require a bit more of a rhombus shape rather than a rhomboid for it to be declared as a diamond, but there you go. Now, another form of parallelogram is, another form of quadrilateral is a trapezium. That's just with one set of lines parallel. Okay, parallelogram requires both sets of sides to be parallel to each other. This just requires one, so that would be a trapezium. And the area for, if I call that A, B, and that H, that's the height. Area equals a half A plus B times height. And when you think about it, that's quite logical, really. It's taking the average of these two and multiplying it by the height. Because essentially, I mean, it might seem quite logical when you think about it, but what they've done in practice is they've sort of taken that bit there and put it on here. So it's sort of more like the formula for a rectangle. And they're saying that that length there is half A plus B, which is correct when you think about it. Just times the other direction, which is height. And again, I think I'll start again. Now this is a kite, okay. And a kite has a property. There's the two adjacent sides are equal. That those two sides are equal in length. Those two sides are equal in length. But also the intersections cross at right angles. That's the definition of kite. But obviously that looks like a sort of a normal kite that you'd fly in the sky. But when you think about it, something like a square is also a kite because that fulfills the property as well. Both a square and a rhombus, because you got this idea of two sides next to each other being equal, which is okay for a square. Okay, and a rhombus. Okay, all four are equal, but that means that any two sides adjacent to each other will be equal. So it fulfills that criteria. And also a square and rhombus fulfill the criteria that the diagonals intersect at right angles. So a square and a rhombus are both kites as well under this definition. So that's really all I wanted to say about the general feature of quadrilaterals. While I'm on the topic, I can probably talk a bit about rotations and reflections, or line and point symmetries. It's dealt with in a bit of a sort of Mickey Mouse way at GCSE level, but you have a take something like a square. If I was to talk about rotational symmetries or point symmetries, I'm talking about, you know, obviously rotating this square about this point, so therefore you've got rotation about a point, so I'm talking about either rotational symmetries or point symmetries. But the thing is that if I rotate this square about this point, when I go through 90 degrees, I'm going to end up with an object that looks exactly the same as this. And I'll go through another 180, i.e. another 90. The same situation is going to arise. So there's 4 positions during rotation. There's 4 positions of this square which will look identical to this view. So I say that a square has a rotational symmetry of 4. However, if I have a rectangle, the rotational symmetry there is 2. I just need to go through 180 to get this a view that looks identical to the view we've got here. That's all there is. It's just after 360, when you're back to where you are started, you've got 2 views which are identical to this. So a rectangle has rotational symmetry of 2. This is the more generalized parallelogram, and that has the same rotational symmetry as well, 2. Go through 180 and it looks identical to the view we've got here. Rhombus. Sorry, this is supposed to be a rhombus. Rotational. This might not be so obvious, but this is 2 as well. Go through 180, you have a view like this again. But that's all there is. So rhombus has rotational symmetry or point symmetry of 2. And the kite, it has to go back through 360 before it has this view again. So that rotational symmetry would be classed as 1. There is the other symmetry that is mentioned at GCSE level, which is the line symmetry or mirror symmetry. For example, this square has a line of symmetry going through here. And basically it's just connected with this mirror views, isn't it? That's just, that view on the right hand side is identical to the one on the left hand side. It's the type of image you would get if you're looking at it through a mirror. So that's what I mean by line symmetry or mirror symmetry. And it also has a line of symmetry here. It also has a line of symmetry going through here and also through here as well. So that has an order of symmetry of 4. Okay. Going through the rest quickly. A rectangle, it has that symmetry and that symmetry, but it doesn't have the symmetry through their diagonals. So that is order 2. A more general parallelogram that has no lines of symmetry at all, so that the order is 0. Paradoxically, when I got to rhombus, Oh, sorry. This indeed does have some lines of symmetry. There's the line going through here and the line going through here. Yeah, because remember that essentially here we've got the lines of, we've got the diagonals, and remember the diagonals bisect the angles and also meet the other diagonal at 90 degrees. So that we've now got two lines of symmetry for a rhombus, so that'll be order 2. And trapezium. In general, you've got no lines of symmetry. But if it's what's called an isosceles trapezium, where that is equal to that, then there is a line of symmetry through there. So that would be an isosceles trapezium if the length of that side equals the length of that side. But in general, for a more general trapezium, there would be no lines of symmetry. And for a kite, you've just got that one line of symmetry there. So questions on this in GCSE level are normally fairly straightforward. You know, it's obviously applies to other shapes as well, but it's not too difficult. It does actually take the subject to a slightly different, a slightly higher level. When we're talking about things like rotating things about at a distance from the axis on a Cartesian coordinate, and taking mirror images across a line and so on. But it doesn't really sort of bring home how powerful this concept is in mathematics. Anyway, I'll leave you that, and thanks if you're still with me. See you again.